Welcome to the next in the series of videos on electromagnetism. In this, we are going to look into electromagnetic induction. So far, we have seen how electric current produces magnetic field. But it's interesting that magnetic field can also produce electric current. So here we have a simple setup where we have these two magnets. So the magnetic field lines are static. It's moving from the north to the south, as is the convention. And here we have these coils wound around a metal ferromagnetic core. You can see that it's hollow, and then we have wound up coils, and this coil is stranded up, and we are taking a wire and then we are connected it to galvanometer, right? Now you can see the effect of there is a magnetic field lines going inside this core or inside this wire. Now, as we put this into oscillation, you can see that the galvanometer needle is starting to move. So you can see that it is oscillating on both directions. So this is the basis of your AC current, wherein the changing magnetic field, and the magnetic field changes because, let's see, when it goes out, the deflection is on the right. And when you let it come in, the deflection is on the left. And similarly, when you go out this side, it's on the right, and when you let it go, it's on the left. So as it keeps oscillating, this deflection keeps happening. And the reason why this happens is because we can understand this reason by looking at Faraday's law. So you have the EMF produced is given by minus N d phi by dt, and this quantity d phi is dependent on two factors. It is dependent upon the area. So let's assume that this is your coil. So this is your area through which the winding is there, right? All your windings are there, and this is the area exposed. And then your magnetic field lines are like that, right? So the magnetic field lines are, let's say, is B, and as this oscillates on both the sides, this area, as it moves out, there is a change in the magnetic flux. The flux is defined by phi equal to the cross-sectional area into the magnetic field strength. So that is your phi. So here in this setup, you can see that phi would be the area of this core into the magnetic field lines. So as I move out this core outside, as a core is moved out, there is a change in the flux. We say there is a change in the flux because at this position, at this position, as it moves, the flux is less than here. So your d phi, which is the change, dt is how fast you're doing it. And n is the number of coils which are wound around this core, right? And the minus sign indicates the fact that this coil doesn't like the changing flux lines. So as you can see here in this coil, as I move out, the flux lines are getting reduced. So the current will be produced in such a way that it will oppose the changing flux. So if the lines are from here to here, and as it is going out, the flux lines are reducing, it will want to establish a flux line from here to here. And the way it does is by passing current in this direction, current in that direction, so that the flux lines in the left are established. Now, as it's coming back, the story is different. So it is getting more flux lines from north to south. So it doesn't like that. So it wants to have flux from south to north. So what it does is it produces a current in the opposite direction. So it produces a flux like this because the flux lines are increasing in this direction. So it opposes, and the current is produced in such a way that it opposes that increase in flux. So that is denoted by this minus sign. This minus sign indicates that the change in flux is opposing the increase in the flux lines. Now I would like to show you one more thing. So here is a neodymium magnet. So I can show you the deflection by just moving this magnet in and out of this core. So you see carefully as I move this in, out, you see the deflection. And if I move it in fast, the deflection is more. If I move in slowly, the deflection is less. So it depends how fast I move, right? I remove fast, so you see the deflection move beyond 10. But if I remove slowly, the deflection is not that much. So that's explained here in the Lenz law. So the dt is a time which makes in which the flux change happens. So if you move it fast, the dt is less, and that's why your EMF is more. So I hope you enjoyed this video on electromagnetic induction and Faraday's law. See you in the next one.